Hi, in this video we are going to talk about backtracking in the main, so let's get started. This is a general algorithm for finding all solutions to some computational problem, such as this is called the constraint satisfaction problem, and we incrementally build candidates to the solution. We don't know the solution in the beginning, so we try to find it, and we incrementally build candidates. And if these partial candidate, for example A, cannot be completed to a valid solution, then we abandon A as a solution. For example, these kinds of problems such as the 8 queens problem or Sudoku can be solved with the help of backtracking. Backtracking is often much faster than brute force enumeration of all complete candidates because it can eliminate a large number of candidates with a single task. Backtracking is an important tool for solving constraint satisfaction problems, such as the combinatorial optimization problems. So what about the method itself? The partial candidates we have been talking about in the previous slide are represented as the nodes of a tree structure. If you are not familiar with tree structure, I highly recommend it. Search it on, for example, Wikipedia, or for example, but it's not so hard to grasp. We build a tree-like structure, and this is what's called the potential search tree. We are going to talk about, by the way, n queens problem in the next video, and we are going to build such a potential search tree. So if you don't understand what's a tree structures, you are going to know everything about it. So each partial candidate is the parent of the candidates that differ from it by a single extension step. And the leaves of the tree are the partial candidates that cannot be extended any further. So the backtracking algorithm traverses this search tree recursively from the root down, and this is a typical depth-first search. We have a graph and we try to traverse it. We could use breadth-first search or depth-first search, although there are several graph traversal algorithms such as the iterative deepening depth-first search, A-star search, and so on, but the depth-first search is very good for these kinds of problems, and backtracking relies heavily on depth-first search. So this is why backtracking is sometimes called depth-first search. For every node, the algorithm checks whether the given node can be completed to a valid solution. If it cannot, then the whole subtree is skipped, and this is why it's much faster than brute force search, because we can skip whole subtrees, and the size of these subtrees can be enormous. And of course, recursively enumerates all subtree of the node. So this is how backtracking works. In the coming videos, we are going to talk about the theory of all of the problems, such as Sudoku, coloring problem, and so on, and we are going to implement it together. Thanks for watching.